Knowing that the couple shown acts in a vertical plane, and so let's depict that plane. So this is the couple. When they say couple, they mean a moment, and the plane would be this one, this 2D plane right here. And so it acts in the same, in a vertical plane. So the assumption is that the two forces that create this couple are symmetric. Determine the stress at point A and point B. So we got point A here and point B here. So this is the cross section. So this view is, if you were to look basically here, that's what that is, right? And so we have these two views. Well, let's see, what can we do? Well, first of all, let's say that this is our horizontal axis, that this is our vertical axis, y. And so here with a point, that's going to be our z-axis. So our moment is happening around this axis right here, which tells us that we will have to calculate the moments of inertia about that axis. So how does that translate to here? Well, think about it. This guy is kind of like, if you were to extend the perspective, it would kind of look like this, right? And so the z-axis is coming out of here, basically, from this view. So what I want you to understand is that now we are calculating the bending about this axis right here. And so we need to know where the centroid is. And there's two things we need to do first. So let's say that this all this material has a uniform density. So let's say that this is our centroid. So this is where our neutral axis is going to be, right? So this is where let me draw a neutral axis. We'll call this neutral axis. That's where it's going to be. Now, how are we going to know where that is in terms of x's and y? Well, if we say that this is our x-axis here, and that this is our y-axis, sorry, I got them mixed up. That's our x, that's our y. Then we would say, if this is symmetric, that this is going to be halfway between 1 plus 2 plus 1 inch. So that would be here, this distance right here, that will be 2 inches. And then we can do the same here. And what would this be? What would this, oh, didn't want to do that. What would this be? Well, we got 2 and another 1, so that's 3 inches right here. So that's where our centroid is. Now, we really just care about the y-axis because we're going to measure the distances from the moments of inertia of this guy and this guy to the y-axis. But really, we don't even care about that in this specific problem. And that's because we can leverage some symmetry and we can do a trick that I just learned. So you see how there's this big triangle, right? Sorry, this big rectangle? Calculate the moment of inertia of this and subtract the moment of inertia of this. And what you get is this moment of inertia about its centroid, because these two centroids of these two shapes coincide, assuming it's a uniform density. So what we're going to do is we're going to say that I total is equal to what? Well, it's equal to this big rectangle, which has a side of 4 plus 1 plus 1, which is 6 inches. And we're going to multiply that by the base, which is 2 and 2. So that's going to be 4 inches. So that's going to be our area. And so remember the formula. We want 1 over 12 if we're calculating from the centroid. And then the height is the one that's going to be cubed. I don't want to confuse you. I'll probably do it in the right order. So if you look at your sheet, you got 1 over 12. And then we multiply that by the horizontal distance. And that horizontal distance is basically that distance parallel to the neutral axis. So in this case, it's 4 inches. And then the vertical distance, the one that's perpendicular to the neutral axis, that's cubed. And that makes sense because the farther the mass is from the neutral axis, the more resistance to bending it's going to have. So it makes sense that the vertical distance in this case will be cubed. So what is the vertical distance of this? It's not a distance, the vertical height of this. And that's going to be 6 inches, and all of that is going to be cubed. So once we have that, that's going to be our first bigger in moment of inertia. We're going to subtract the small one. So the small one's going to have 112, and then we have the 2 inches for the base and the 4 inches cubed for the height. And so now that we have this, let me just take the time to input this into the calculator, and we're going to have 1/12 times 4 times 6 to the third minus 1/12 times 2 times 4 to the third. I just got to make sure I input this correctly, and I get 61.3 inches to the fourth. Okay, so now that we have that, what are we going to do? Well, we want to know the stress at this point and at this point B. So we know that we're going to get some sort of bending around this neutral axis. So we want to know this distance, which we've already seen to be 3. And then we want to know this distance, which is, this whole thing is 4. We know the neutral axis is at half of that, so at 2. And so this is 2. And so now that we have that, we can go ahead and use our formula for the stress in what direction? Well, look at this. The stress is going to come out of here. It's going to be some sort of distribution, right? And so it's going to be along the x direction. So the stress along the x direction is going to be equal to the moment. The moment is about the z-axis, so we'll put a z-axis. We're going to have a distance, y. Then remember that it's negative, and that's because we define y as being positive up, and that would create a negative moment. And we divide everything by the moment of inertia of the whole cross-section that we calculated earlier. So now that we have this, we're going to take the moment, which is 200 kilopounds per inch, times y, which in our first case, it's 2 inches. That's for A, at the point A. And we're going to divide by 61.3 inches to the fourth. And now that we do that, I'm going to get 200 times 2 divided by 61.3. Well, that's going to be 6. That's going to be 6.52. And that's going to be, what is it? Kips and over inches squared. So K is psi. And now we need to specify. We got a negative value, didn't we? I forgot a negative in the calculator. So this means that this is in compression. And so now we can box our answer right here. Now we can do the same with B. Now what do we expect from B? Think about it. Well, if you said tension, you're correct because, well, first of all, if there's compression on one side, there's going to be tension on the other side of the neutral axis. And then we're bending it like this. So this side is going to get shorter. This side is going to get longer. So it's going to be pulled apart, right? So let's say now that the sigma x about the point B, well, that's going to be the same formula. So minus mzy over I. And that's going to be equal to what? Well, it's going to be equal to negative. We're still going to have 200 kilopounds times inches times 2, well, 3 inches now because we're going down, and we're going down, so it's going to be negative 3 inches divided by 61.3 inches to the fourth. And now that we have that, we can input it into the calculator and see what we get out of it. And that's 9.79 KSI. And that's going to be in tension because it's positive. So that's kind of a recap of the little problem that we did earlier today. I wanted to do this video because I did not get it right, because I did not think of subtracting the two areas. So I was doing the moment of inertia of this guy, this guy, this guy, and this guy, and then trying to apply the parallel axis theorem to the top ones. And somewhere along the way, I should have gotten the same result, but somewhere along the way, I made a calculation error, ended up getting the wrong answer. So yeah, but now I understand. I hope this was helpful, and I'll see you next time.